the next step in our series of supervised techniques, and already a little bit less simplistic. We saw logistic regression, decision tree, and KNN. Now we come to the kind of the style or the type of techniques that's still being utilized a lot. What's the basic idea there? The basic idea is the fundamental question: if I have two models and I combine them, or I would find a way to combine them, would that then work better than using one model separately, or using each model separately, right? Basically, the question that you ask is, if I take these two predictions that I get from these two models, and I build like some sort of model on top of that, would then the outcome, would there still be some improvements to be gained there? And maybe intuitively you say, well, this doesn't make sense, right? Why would it be? If that would be the case, then why didn't that model already pick up on that to begin with, right? But you might also say, well, depending on what these two models are, this might actually happen. If maybe model one is very good at some segment in my data set and the other one is better at another segment, then they both have like separate capabilities and they're complementary, right? And I can combine them in some way perhaps. So yes, maybe to increase performance is a reason why we would do that, right? And of course will be an important reason because we love accuracy and we love performance. You could also say, well, this is a little bit similar to the typical jar of jelly beans experiment. If I ask one of you, guess how many jars or jelly beans that there are in this jar, you'll probably be far off, but if I make a distribution of all of your guesses, the average will be pretty close to the real amount that's in that jar. So maybe that's also a way where all of you are a model and you have given me a prediction, right, in a regression context. And also there I do see that by kind of averaging your predictions, I get a result which is better, right? More stable, less overfitting even, in a way, right? Maybe asking 100 people gives you like a better spread and distribution than just asking one person as well. So also there it kind of makes sense. So yes, indeed we will see it does make sense and that's what we will do, both to increase performance, but also, and that's maybe even more important, I would say, is to prevent overfitting. And that's maybe a bit strange, right? But in a way you might say, well, if you do encounter a strange case, the fact that you asked multiple opinions, right, might then prevent you to lead more kind of crazy mistakes as well. What we will call this, if we combine models together in some form, we then call this an ensemble model. Ensemble, French, together, so this is called an ensemble model. So why do we need it? Well, in some cases, what we saw from our decision tree discussion, we couldn't have it both. If we went too far, too deep in the size of our tree, then yes, my trained data is perfect, but I become worthless on unseen data. So I would like to have it both, obviously. I want to get a great performance on both my training data and on new data, but like this I can't get there. So we could stop, but then, yeah, I might be happy at that point, but in this case I might also say, yeah, but the accuracy is still not that great, and also if you look at the decision boundaries, the accuracy is not that great because with this early stopping, this complexity plot again, you have just made your model a bit more biased, a bit more simplistic, right? But I don't want a simplistic model, I want a complicated model, but one that's not overfitting, right? You could also think, well, if you use a linear classifier, it's even worse there, because if you give a linear classifier this kind of data, well, it's going to draw this line, but you've basically just ignored this whole group of positives over there, right? So maybe here you would actually want to say, I want to build multiple linear classifiers and put them on top of each other in some way, right? Is that something that you could do? So what are ways to combine models? Well, whenever you have predictions of submodels, you can make a meta model that combines their predictions in some way. All possible manners of how you would combine two or more models together are okay, as long as you can apply that strategy that you have on new data points, right? And that you have validated that your strategy actually works on unseen data. So what are some ways that we could do? Well, here I have two models and they've given me predictions on a bunch of instances. And they're both not bad, but they both make, sadly, still one mistake, right? And model 1 makes a mistake here, and model 2 makes a mistake there. These models give me probabilities, scores, right? And I've already kind of figured out the best threshold to use for each of them separately to maximize accuracy. Right? You can try yourself to try another threshold here, but you will never find a better threshold than this one or this one. Right? And sadly, I still make one mistake for each of those models. But they do not make the same mistake. So that's already something that you see here. So simple things that you could do are, well, if I just take like a simple mathematical combination of these predictions that I have, and I take the minimum or the maximum or the mean, then effectively you've created a new model, a new ensemble model that uses the predictions of these two other models. Because this combination is its own new model, right? You again need to establish a new best threshold on that combination, right? And then you see that there are things such as taking the average of these two, and then with this threshold, suddenly all the mistakes are gone. Right? Oh, well, so great, easy way. It would then indeed indicate, well, min and max, they don't seem very stable, right? But taking the average of probabilities, yeah, that's a way, right? How you can combine models together. What's a simpler way is not averaging the probabilities of your models, but by saying, well, each of them gets a vote. It's a yes or a no, and the majority wins. Right? So here I have 6 models. 4 of them say that it's a yes, so yes wins. And I could even give like a probability, quote unquote, or a score. I could say, well, my final probability is 4 out of 6, 66%, right? Because 4 out of 6 models agree. It's again not a well-calibrated score. It's based now on models. It's not based on instances in a leaf node, but it's based on models in my ensemble that have agreed. Right? But okay, it's also a way how we could rank. If all the models agree that it's a yes, then probably that's a stronger prediction. Now you might also say, well, but what about these are 6 models, but they're not all as strong, right? Maybe some models are weaker than others. So maybe we should not all give each of them 1 vote, but we should kind of use a weighted voting scheme instead. Could you do so? Yep, sure. That's basically a linear combination of the probabilities. Sure, why not? But of course, then the question becomes, you've introduced parameters, how much votes should each model get? And that's something that should be learned in itself, right? So now you're meta-learning, you're learning something about your learners, right? So you're meta-learning. Rarely done, or less frequently done, obviously. One of the fun reasons why this is rarely done, but I will get to that, but one of the fun reasons is that once people, and especially managers have a tendency for this, I don't really know why, but once they figure out that your final prediction is done in this way, where you take submodels and you give each of them like a score, people are going to want to decide the scores for these things themselves. People love handing out number of votes to things, also to models. So not a lot of meta-learning, but more like manual tuning, you could say, happens in real life when people utilize this, but okay, fine. But that's exactly the idea of a mixture of experts model. So you start with a bunch of classifiers, and you're going to make a linear combination out of their predictions. The question is how to assign a weight to each of them, and here expectation maximization is utilized to optimize the weights out of this thing. Right? You could also actually use something like stochastic gradient descent even, that would work as well, doesn't really matter that much, but this is exactly that idea. A similar idea is to use stacking, and this is popular in Kaggle competitions where people really want to squeeze the last tidbits of performance that they can. And this basically says, well, start again with your bunch of classifiers that you already have. They make their predictions. So you start with an instance or with a data set with its features. You have a bunch of models, model 1, model 2, and so on. And each of them gives you a probability value, 80%, 70%, 60%, and so on. And then you say, well, out of these probabilities, make a new table. Probability of model 1, probability of model 2, probability of model 3. Stick in these probabilities, and now use these as features for the meta classifier. The classifier that's going to classify how much importance each model should get, depending on the 3 probabilities that we see, right? here that meta classifier, if that thing is complicated enough, can even be something now, and that's the benefit of using stacking over a mixture of experts model. In a mixture of experts model, all of your models ultimately get a final weight assigned to them, right? But the weight here is dependent per classifier, not instance. This will say, well, classifier 1, you get 20% of the votes, and classifier 2, you get 10% of the votes, and that stays fixed. In this setup, your meta classifier could technically learn to reason, if these two guys both give a high score, then the opinion of this third guy basically doesn't matter. But if these two guys give a low score, then it's the opinion of these two that I should take into account. Or then this one gets the decider vote, right? Whatever that goes on. I don't know, right? Whatever structure appears there, but you retain the capability to learn that. Only, of course, if your meta classifier has sufficient complexity, right? And then again, what you lose is interpretability. Because, of course, if people ask, okay, how are now the scores of these three models combined with one another, mixture of experts is easy to understand still. Here, if you say, well, then we put like an XGBoost model or a decision tree on top of that, and that can go in all sorts of directions, harder to understand. And probably will also overfit more easily as well. You could then even say, some of you are already thinking this, I'm sure of it, but wait a second, the fact that this thing is pretty complicated and can get pretty smart, why wouldn't we also, when we built this meta classifier, why would we train it on these three predictions only? Why not reintroduce the original set of features in here as well? Because then this meta classifier can learn, given which instance or type of instance we are looking at, who of these three should I believe more, right? For boys, it's model 1 that's often right, and for girls, it's model 3 that's often right, right? All of that's possible, but you lose interpretability very quickly. And it's also harder to maintain this whole stuff in production as well. But like I said, on Kaggle competitions, people like this approach. And then these models are very often XGBoost, LightGBM, CatBoost, Random Forest, and probably neural network for good measure as well. And then the meta classifier on top of that, well, then you do need to make a choice again, right, what you end up utilizing. So then you pick your favorite technique and one with a sufficiently high degree of complexity. Another thing where it kind of makes sense to do so, not very common, but like as a fun example, is if you already have a model that itself is pretty complicated and might itself be an ensemble model, evidenced here by kind of the very detailed decision boundary that goes all over the place. Maybe this is a decision tree that's pretty deep, right? It's not an overfitting one. Let's say that this is test data and it's doing still a good job on test data, right? But again, there is an issue of potential extrapolation from the training data. We know that we can never avoid that, and we should monitor, but we can try to fix it a little bit. And especially this is nasty, right? Because this is an area in our training data where there weren't any training points. So our model wasn't able to learn anything here, basically. And what does the decision tree do? Well, it will predict you, in that case, the majority class, right? So it will say, well, everything which is here is blue, basically. Now, for us, if we see, well, we basically would say yes, but this is kind of an extent of this red tail. So wouldn't it be more logical to say red there, right? And again, what you could do is you could take the distance to your known instances and use that as a guide, for instance. What you could also do is say, well, let's build logistic regression, and let's again average the predictions of both. But this one gets a way higher weight than this one does. And so this at least helps us to both smooth out the decision boundary a bit, but also to maybe avoid some extrapolation effects like this, right? Not perfect in all cases, and again, it works better with a 2-dimensional example than with a 100-dimensional one, obviously. But a nice idea that's also pretty clever. Okay, so then, bagging. Bagging stands for bootstrap aggregating, and is an alternative approach to make, or well, alternative, is an approach to create ensemble models, but now not saying, and this is the idea now that we will kind of explore, so far what we did is we took models that already were there, and we found out a way to combine them. You might also think about, but isn't there like an algorithm, or algorithms, that built the whole ensemble for me directly, that I don't need to come up with 6 or 3 models, but where the algorithm itself leads to an end result that is not a single model, but which is an ensemble of models. So the algorithm itself constructs multiple models directly. And so yes, it exists, and one of the ways how to set that up, well, you have 2 main ways. One is called bagging, the other one is called boosting. And we'll start with bagging first. Stands for bootstrap aggregating. Bootstrap aggregating has nothing to do with boosting, which we will see later. Bagging stands for bootstrap aggregating. The idea here is that we will add diversity to the classifiers. So we will use the strength of diversity here, and we will do so by making bootstrapped replicas of the training data, which is how we add in variety. Okay, let's take a look. What does that mean? That means that you start with your complete set of training instances, and you're going to build n models. N should be large enough, right? But 3, 4, 5, no, more, 100, right? But 100 doesn't really fit on the slide. And each of these models, we're going to try to reach more diversity. So how do we do that? The idea is that we take a bootstrap aggregate from our training data, and that is just a fancy way to say we take a sample of our training instances, but a sample with replacement. So an instance here can either not show up here or can show up multiple times here, right? How large is the sample? By default, people have said, well, the number of instances here is the same as the number of instances that you had to begin with, but not the same instances because we sample with replacement. Right? Now, you might say, yeah, but if you already have millions of instances, why make it always so large? Maybe we can also make the sample smaller. Yeah, sure, you could do that, right? But we sample with replacement. And that's the whole thing about bagging. That's it. Then you understand bagging. You're done, right? Then we just say, okay, now train a model for each of these samples with replacement. Oh yeah, at the end we still need a way to combine them. Well, let's say they all give probabilities. Let's use majority voting, right? Or let's average their probabilities. It's also something that you could do. It's actually an interesting question. I think it's repeated later on, but we can also already mention it now. You might wonder, yeah, but majority voting, wait a second. If you have 3 models here, or 100, and they give you probabilities, 70%, 80%, 30%, to do a vote, you should first convert these probabilities to predicted labels. Is this a yes or is this a no? And you've told us before that we should set a threshold for that, but that how you set that threshold should not always necessarily be at 50%, right? So does that mean that we need to here pick the same threshold for every model, or that we tune it for each submodel? Well, please, I hope not, because that would be a lot of work, right? For now, we could simply say, well, let's do either the following. Let's say the threshold is 50% for everybody, right? So then this is a yes, this is a yes, this is a no. 2 out of 3, probability 2, or my final probability. Or you could say, no, let's average the probabilities instead. Then you also sidestep this issue, and then that is your final output, right? Later, we will see that the issue of that thresholding is not really an issue, but for now, you might think, ah, yeah, that's a bit strange, right? So maybe averaging the probabilities instead of majority voting is more likely. What is also strange is that taking these samples helps in any way, right? What's the benefit of doing that? You're kind of cheating with your training data. You're not including everybody even. So what's the benefit of this? The benefit is that, for instance, think about an instance that's very noisy or very difficult to predict or very skewed. The fact now that this will not show up in all of the bootstraps will make the model overall more robust against such noisy factors and noisy elements. That's the benefit of bagging. That's the benefit of trying to add in a bit of diversity, right? So that you have models that see the noisy instance, but also models that do not see the noisy instance. And by averaging their predictions together, you can avoid being more sensitive to these kind of noisy outliers and so on. Okay, you can believe that or not. We'll see later that it is actually true. Another question is, train these models, but which algorithm should we utilize? Should that be a logistic regression or a neural network or whatever? In fact, bagging works with anything. We haven't spoken about what this classifier should be. Ideally, you use the same algorithm for each of these models, right? If you say, well, I'm going to bag and I will construct 100 models, they should all be 100 decision trees, for instance. I'm not going to mix. I could, but it doesn't seem like such a good idea, right? What do people utilize? Well, in most implementations, or the cornerstone implementation will tell you, you utilize a decision tree. That's the best one to utilize. It's the best one because it's already less sensitive to outliers. It's the best one because you get interaction effects for free, you get nonlinear effects for free. We saw that it has a lot of nice properties, so it seems to be reasonable to utilize those. Another reason to utilize them is that because we want variety, if you think about it, we are creating samples here from our data, but it's not like it's really an extreme change that we are making, right? Especially if the size of a sample is as large as the size of the training data. Yes, there will be some instances that appear 2 times, 3 times. There will be some instances that are not included. But all in all, the difference or the similarity between the bootstrap and the original training data is relatively similar. What's the learner that will lead to the most differently looking models, even after having introduced slight changes to the data? We saw last time that that is a decision tree, that was an unstable classifier. Right? So that's why we also want to utilize it here. We want to pick the technique that's most sensitive to adding in diversity like this. So all these decision trees that you get here will look wildly different from one another. Right? And that's exactly what we want. We want to add in variety. So majority voting, and then just use 0.5, already mentioned, or we average the probabilities. Yeah, could you do this with regression? Yes, sure. Right? With regression, you typically then average again the predictions of all the base learners. And it's pretty funny because in the case of a decision tree, the prediction of each individual decision tree was already an average of the values of the train instances that ended up in that leaf node. So you're kind of averaging averages here in this case, right? But that's something that you could do. And again, you could think about cases where you say, could I then kind of get confidence intervals out of that by looking at this a bit closer? Or in the case of binary classification, if there is a tree and it gives me a prediction, but the number of elements in its leaf node that reaches or that leads to that prediction is very small, then maybe that tree should play a lesser role. Interesting things that you could think about here or could explore. Say a little bit more about it in a second that maybe prevents some of these approaches. But for now, let's just say every tree, give me your output M, let's average it, basically. Either the probability or the regression, the continuous value. Scikit-learn, contrary to the original paper, also for binary classification, averages the probabilities. Another nice thing that we get for free by bagging is because now in every bootstrap, not every instance is contained. That means that there are decision trees in this setup that given a certain instance I in my training data, that not every tree has seen this instance during training because it might not have been selected in their bootstrap. So that means that even without creating a validation set or a test set, I can already get some estimate of performance on unseen data by asking my trees what they think for every instance in my training data, but only asking those trees that did not have that instance in their bootstrap sample, because to them it looks like an unseen case. It's not exactly the same because you're working with less trees when doing this than the full set of trees to average their probability, so it's not, again, a complete or perfect estimate. But this so-called out-of-bag validation, or OOB validation, already gives you a good initial validation check as well. So it's nice that they also give us this kind of a validation mechanism for free as well. One implementation of this whole bagging idea that kind of instantiates it a bit further is random forests. And that's the bagging technique. Right? You could do it with logistic regression or whatever, but the choices that were made here work the best. If you understand bagging, how much more work is it to understand random forests? Basically very little work. There are basically two extra things that you need to know about. And the first extra thing is, remember, bagging is all about adding variety, it's all about adding diversity, so it's all about playing with randomness a little bit. One way how bagging adds in randomness is by working on the instance level, by not having or by not letting every classifier see every instance, and it did so by means of these bootstrapped samples. So that's the first way of adding in variety, bootstrapping. But you could think of other ways as well, right? Another way how you could think about it could be, well, why do I also not limit the features that every tree sees? I could sample the features as well, right? But typically that's a little bit more limiting. You don't have so many features in all cases, so randomly completely leaving out features for a model, that's maybe a little bit too much of the good thing, right? A bit too much variety maybe makes it more noisy overall. But there is like a softer approach of this that we can apply. And that's the approach that random forests add, right? So the second randomness is feature sampling. But how? In a decision tree that we are building, and remember, we are not building one, we are building hundreds of them. The decision tree already works with a bootstrapped sample. All right, that stays the same throughout the whole building process. But now in the for the second part of randomness, at every split of the decision tree, so not for the whole decision tree, but at every split that we are figuring out, sample a percentage of the features. And in the most extreme case, you could say, well, sample one feature. Not with replacement here, right? Just normal sampling. So pick some features at random, and those are the only ones that you can look at in this split. So in this split, you can look at feature 1, and feature 3, and feature 10, but not the others. But then later on, like here, we sample again, right? So here maybe we look at feature 1, feature 2, and feature 5, and so on. Never tell me that in random forests, the features are sampled per tree, right? They are sampled per split of the trees, never per full tree. You could do that, but it's going to work less well, right? That's the second part of randomness that random forests add. So there are two hyperparameters that you need to configure. The number of trees in your ensemble, but actually you don't need to tune that. The answer is just set it large enough. Not 10, like in SPSS from 98, 300, something in that ballpark. High enough, a lot of trees. Second parameter is how many features to sample in each split. The defaults there work relatively well. Even if you don't use feature sampling, it will work relatively well. If you set it to 1 and you build enough trees, it will work relatively well, right? So you can tune this, it does have an impact, but it's also not like an impact like with some other modeling techniques that it can really break or make your results, right? So even if you don't tune and you use the defaults, you will typically be okay. Yeah, I guess a third hyperparameter could also be the size or the length of this bootstrap. If you have a lot of training data, this could be smaller than the instances in your training data. You could also tune that, but the default is also fine. You can keep it large. And that's it. This setup makes this so robust to overfitting that in the random forest implementation, you still can if you want to, but you don't have to apply pruning or early stopping anymore. Meaning that now every decision tree that we built in this thing is itself a horribly overfitting decision tree on its bootstrap. And it's just by the mechanism of averaging their predictions that we get rid of the overfitting. And you get best of both worlds. That also means why I said previously that the discussion on setting a threshold per tree does not really matter in this case. Why doesn't it matter? Because in every leaf node there is a single instance now, except in extreme cases where you have so little features that you still end up with a fully constructed tree, but still with leaf nodes with multiple instances. That could happen. But if you have enough features, typically every leaf node will have one instance in it. Reasons to still prune is to speed up the thing, not to prevent overfitting, not to make it better. Here, simply because you might say, well, I don't want to fully build the trees, that takes too long, right? I need to build 100 of them, so I don't want to do that. But you don't need to. And random forests work very well in most cases, right? So these are the hyperparameters, already discussed a bit. The defaults are there. For the size of the subset of the features, a good heuristic is just taking the square root of features that you have for classification or dividing them by 3 for regression. Don't ask me why they decided to divide by 3 for regression and taking the square root for classification. Probably this is folklore, and maybe just one guy found out that this worked relatively well, and since then it has stayed the same. But you can tune it if you want to, but very often the defaults also work pretty well. So they're very easy to use. You don't need to, or you don't introduce a lot of hyperparameters. They're very good at overfitting by design. The only thing that you kind of lost is now your final model is 100 trees. You have lost your interpretability part. A single decision tree you can still explain to someone, they can understand what's happening. Now 100 decision trees, you have now made a black box model, right? There exists extensions that add in even more randomness. Extra randomized trees, for instance, they add in a third piece, or you could actually call it, they have a 2A and a 2B, right? Not just feature sampling, but also split point sampling. What is that? Well, remember that here we might have a feature like H, which we selected, but for H, we will still test all possible rules. Is H lower than or equal than 18, 19, 21, 25. All the values that we saw in our training data will be considered as possible splitting points. You remember that from before. We calculate the information gain for each of them. Blah, blah, blah. We pick the best one, right? Well, if we randomly take out some features, why wouldn't we randomly take out some of these values that we saw as well? Ah, yeah, okay, fine, makes sense. Let's do that, right? And that's what extra randomized decision trees then add in. They tend to work a little bit better even than random forests, but not like to an extreme extent. But it's a clever idea. We will even see an application where we randomize everything. We take a random sample, and then in the decision tree building itself, we don't even utilize information gain anymore. We just say, pick a random feature, pick a random splitting point, that's your split. Don't check anything, don't calculate information gain, don't calculate entropy, just take a random feature and a random splitting point. How would that ever be informative in any way? Well, we see an application where we do exactly that soon, right? If you work with isolation forests, that's exactly what you do. For predictive contexts, although there have also been papers that show that even from such completely randomized trees, you can make an ensemble model that's still predictive, believe it or not. So even in predictive cases, they can work. but less common because then you need way more trees, typically. So this is a good mixture between randomness and performance. That's bagging, that's random forest. And that's also time, actually, for our 15-minute break as well. And then we will discuss boosting. Okay, boosting time. From a bit far away, a bit similar to bagging, because here we will also end up with an ensemble of models, and very often we will also use decision trees as the base learner, in the case of boosting as well, but a bit fundamentally different. One difference with bagging is we're not going to use any bootstrapping, so no sampling with replacement. And the main idea here is also not to add in diversity in our data, but the main idea is cooperation, you could call it. Fixing each other's mistakes, if you will, strengthening each other. So how does that work? Well, here it does depend a little bit on which exact model algorithm that you look at. With random forests, that was an easy extension of bagging, because random forests was everything that bagging does, plus some extra things. Here, the way how boosting works does depend a little bit on which particular algorithm that you look at. So we'll start with kind of the simplest explanation first. What is a way how we could go for cooperation and fix each other's mistakes through boosting? So again, we start from the whole training data. This is not a bootstrap here. This is just the whole training data. Right? I'm not using sampling. This is the same data. But what I do here is, let's say I come up with a mechanism to assign weights for each instance. And of course, in my first starting round, every instance will get the same weight. Every instance will be as important. And I build my decision tree or whatever model that I like to use, and I test it out on all of my training instances. And some of them will be mispredicted, some of them will be correct, right? And I utilize these mispredictions or these mistakes to update my weights. And obviously, the more wrong or incorrect my model is, the higher the weight of that instance will become for the next round. You already spot, or you might already kind of feel, some crucial aspects here. And one crucial aspect is that obviously this whole setup is not going to work if we again utilize a decision tree that we let build all the way. A decision tree without pruning would not work here, because that decision tree would perfectly memorize the data and would not make any mistakes to begin with, even after the first round. It would just lead me to a single horribly overfitting model. So here, I kind of need to make a choice to keep my models deliberately dumb, right? So that they don't directly immediately overfit. So here I will use a decision tree, but where I do apply early stopping or pruning, or I maybe heavily limit the depth of the tree, right? So that's something that I will have to do. So then it will make mistakes. I update my weights based on those mistakes. And then there is another tricky part, and I build the next tree. And basically I need to give that tree an indication of saying, but be careful, try to focus now more on the instances that got a higher weight than the others, right? Those are now more important. How do you do that out of the box? Also not that easy, right? Again, we have seen previously we could fake it a little bit, and we could just say, well, maybe based on the weight, we could make copies of instances. And so the more important an instance is, the more we're going to copy it, and that will basically bias our decision tree to pay more importance on that instance. Yes, that's a way how you could kind of wiggle your way out of that and implement that, right? If you don't know any mathematics, that's how I would do it, right? So, okay, there is a way how we could use that weight to steer a learner. That seems reasonable to us. We could do it that way. So, okay, fine. Then we have two trees. And again, we use majority voting, or we use average of the probabilities, same thing. And we then let this mini ensemble of two models, again, score each training instance. And again, we look at the mistakes and we update the weights. And we continue and we continue and we continue. And that's what boosting does. And this is, for instance, what AdaBoost implements. It's exactly this algorithm that I just described. Don't need to memorize this algorithm. I mean, it's not that difficult, but it starts by giving every instance the same weight. Obviously, you need to. Then it trains a normal classifier. Each learner is also given its own weight, depending on its accuracy. That's something extra that this does, that also every learner gets its own weight, right? But you don't really, well, makes sense to do that, but you don't need to know that to understand the mechanism of boosting. And it uses the weights so far every time it constructs its new learner in every iteration. And that's basically it. That's AdaBoost. Now, this has issues. Potential issue is, well, if you compare it to bagging, maybe you already see a couple of them. Like one issue could be that you start to wonder, yeah, but when do you stop? Right? You probably stop when you see that your mistakes are low enough. But again, you are always working on the same training data. You can kind of feel that, okay, even if you use very dumb models, if you stack enough of them on top of each other like this, if you boost enough, at some point, we will probably end up overfitting the training data anyway, right? So there is probably a point in the middle where you need to stop as well, right? After 100 trees like this, you need to stop and not more. With random forests, I kind of said, well, just use plenty trees. There is no risk of overfitting there. So that's already one difference. It's like we don't completely solve overfitting here. Right? But we do try to go for a better performance, and whilst trying to avoid overfitting. So that's one thing. Another thing is that, yes, this AdaBoost algorithm, this is very specific to some choices that have been made. The fact that how this alpha here needs to be calculated, that's basically what makes this whole setup work, right? That's basically, and also the weights, how these are updated, it's e to the power of minus this alpha times each learner. So I told you that, yes, you could use these weights to copy instances. That's a bit of a dumb idea. This formula is probably what makes it work mathematically with in this setup. But yeah, it feels a bit strange in the sense you could wonder, like, okay, what is this now actually optimizing by doing this iterative procedure, right? What is this kind of trying to improve round after round after round? Why is this now fixing the mistakes? So people saw that it worked, right? But kind of the mechanisms behind it were a bit kind of vague and a bit kind of arbitrarily chosen. And so a researcher called Friedman and some others, they also thought that that was a bit annoying, that there were some specific choices that were made for AdaBoost. And so they said, okay, let's take a look at that, and using they're way more clever people than I am. So through some mathematical derivations, they basically found, okay, what you're actually doing here, or an equivalent procedure that would end up in the same result, is additive logistic regression. So you use logistic regression as the base learner then, not decision trees, but logistic regression. And just like in additive logistic regression, what you actually optimize is the exponential loss function. That's what AdaBoost optimizes. And you could say, well, this is just a little bit of mathematical prowess in the sense that, okay, fine, you have shown that AdaBoost is now equivalent to something else, but so what? And they said, oh, well, the so what is that AdaBoost is closely linked to a particular choice of loss function that it is optimizing. And you don't have kind of flexibility to change that, right? It is the exponential loss function that's being optimized there. So AdaBoost produces an additive model. The way how they wrote it is a bit passive-aggressive. AdaBoost produces an additive model, although weighted committee or ensemble sounds more glamorous. Not so nice if you're the authors of AdaBoost to hear this, but anyway, your paper is already published, so who cares? But that's what they showed. But they didn't stop there. They then said, okay, but now let's make it interesting. What if you still want to use something like boosting, right? And you like AdaBoost and you like the way how it works and it gives you good results, but you want to change the loss function. You want to use a different loss function. instead. Then you need to change AdaBoost because it's not going to work anymore. Right? So how do you do that? How could you pick a different loss function and set it up using AdaBoost or additive logistic regression? Neither of these would then work. So is it then still possible to make boosting work? To make that whole idea of let's iteratively fix the mistakes that we are making so far, to actually have that work with any other loss function than this one? And the answer is yes, you can. And what they said is what you need to do is you need to take a different view. Instead of trying to weight your instances or weight your classifiers based on mistakes that you are making, take a different perspective. And instead, what you could ask every new classifier that you add to the mix to do is to predict the residuals that the ensemble as a whole is producing so far. Learn to predict the mistakes directly. Learn to predict the errors directly. Because if you can predict the errors well, you can correct the predictions of the previous ensemble so far, right? If you predict 10 and I know that you're predicting 5 too high, then I can basically derive, okay, the real prediction is 5, not 10, right? And if you do this, then you don't need to use AdaBoost, you can use different optimizing schemes, and you can use any loss function that you want. Now, why does this work? Why does learning the residuals allow you to then utilize a different loss function? Because the residuals for a given model are closely linked to the negative gradients of the MSE loss function. This is MSE, right? If you take the partial derivative of that according to the model, you get this expression with H being the residuals. So your residuals, if you try to predict those, you're basically improving MSE, right? That's what you're doing. And for other loss functions, right, you can also derive the gradient from that, and you can also then optimize on that in a similar way. So then you get flexibility to plug in a different loss function, calculate its gradient. There will be an expression that uses the residuals in there. And then basically, once you can predict the residuals, you have everything that you need, right? If you know what H is, you know the gradient, right? And for other loss functions, similarly, there will always be a component in there which are the residuals. So if you know the residuals, you know the gradient, both for MSE, for log loss, for cross entropy, for focal loss, for hinge loss. The residuals will show up as a component there. So once you predict the residuals, you can calculate the gradient. And that is why this scheme, or this setup, why this is called gradient boosting. Each learner that you add in every iteration learns to predict the residuals, and so you can then use their predictions to improve upon the gradient or to follow the negative gradient of your loss function. And you do that in rounds, and that's a gradient boosting machine. And this today, apart from random forests, is the most popular technique for tabular data, is gradient boosting machines. If you combine both random forests and this together as a group, these are called tree-based ensemble techniques. Right? And you have bagging on the one side with random forests, and you have GBM on the other side with boosting that it uses there. Now, this is made popular by techniques such as XGBoost or implementations such as XGBoost. Why XGBoost? And here it's GBM, XG, extreme gradient boosting. That's not just marketing, right? Extreme gradient boosting is then an expansion of this idea where they not only just use the first partial derivative, but they also use the second partial derivative, right? Because the first partial derivative gives you the direction that you should move in, but not the size of the step that you should take, right? If you also want to know the size of the step that you need to take across your loss landscape, you also need the second partial derivative, right? This makes it go faster and work better. You could also say, yeah, think about this, a bit strange if the second partial derivative of the gradient, so both the Jacobian and the Hessian, if those together work so well, why in deep learning are we still using the first partial derivative only? You can look that up, actually an interesting question. Whereas in XGBoost, we use both. Now this idea of gradient boosting machines is what's implemented in the 3 most popular libraries packages today: XGBoost, LightGBM, GetBoost. They're all a little bit different. XGBoost can train even on the GPU, actually also has a random forest implementation, so it's actually both boosting and random forests, has a couple of extra interesting tidbits in there, has a lot of hyperparameters that you can play around with, is extremely popular. Can in some cases be relatively slowish, especially if you have a high amount of data and features, can suffer a little bit from that. LightGBM is a way, or is a mechanism that implements gradient boosting, but first bins all the data that you have in bins, right? By making histograms first of all the features and then working over the bins to speed up the procedure. It also always creates a bin specifically for missing values. So with LightGBM, you don't need to treat missing values. And GetBoost is also a pretty similar idea, but again allows decision trees to make non-binary splits for categorical features, but then adjusts the information gain measure to not be biased anymore on this. Right? But it's also a boosting-based technique, but it can deal a bit better with categorical features. So they all have their strengths. They are not exactly the same. Very often, in industry settings, you see that people have decided on their favorite out of these 3, and they use it all the time. Whatever new tabular task that comes along, they utilize one of these 3. Right? And rightly so. In most benchmark studies that are performed nowadays, these win. Right? In studies where they even compare this with the best deep learning-based approaches on tabular data, these still win. Might change in a couple of months, who knows, right? But these still win. On most Kaggle competitions on tabular data, one of these or all 3 of these will be utilized, right? So they are extremely important and powerful techniques. Even so much that for many, well, even so much that it sometimes happens, and we have seen cases like that, where you see studies in like particular domains, and like we currently see this in geospatial statistics, where they use geographically weighted regression and kriging and even adaptations of random forests in newer papers to deal with regionality and so on, that they do not compare in their experimental setup with these techniques, and that if you would compare with those, that these would simply win. So they're very powerful techniques. I used to like random forest a little bit more. I still like it a lot for the reason that it has way less hyperparameters, and for the reason that it's a bit more protective against overfitting. But I can also not deny that in like practical settings, if you really want to get like a good baseline model with excellent performance, these are very good. One drawback is, again, it's a black box model. You lose interpretability. And yeah, this overfitting thing, it is there, right? If you use boosting, you're not fully protected against overfitting. So that's a little bit of a danger that's still in there. So what most models also do is they add regularization, for instance, again, to improve generalization capabilities. And the way how XGBoost, for instance, does that is defined over the depth of the tree or over the number of leaf nodes. So where you say, okay, you can add in more leaf nodes, but the more that you add, the more complex that you want to make your model, the more that the benefits need to be in MSE, otherwise you're not going to do it. Other nice or cool ideas that you can do with this, so these are extremely versatile, smart models. Decision trees are great, especially if you use them in boosting. This is something that XGBoost also implements, and this is Dart, which is the idea of dropout, which we will see in neural networks. And dropout means that you randomly take out neurons during the training of your neural network. And again, that sounds strange. Why do you randomly take out stuff from your model during training? But it helps because it forces your model to learn redundant pathways to fit the data. Also here, DART means you use dropout, but here you drop out trees. So whilst you're adding trees, you also randomly take out some trees from time to time. You add them back in afterwards, but maybe in some rounds, some trees do not play along in the ensemble. And this also avoids overfitting. So that's DART. Another cool thing that you can do is, since decision trees capture feature interactions and features that show up in a pathway together or likely to interact with one another, you can constrain this behavior. And you can, for instance, say, well, I know that these features are not interacting. They're not allowed to interact, so they cannot show up together in the same pathway in a tree. Very easy to add that in. Gives you extra power to kind of tweak how these things learn and build themselves. Another constraint that you can add in regression cases is to say, okay, if you look at this feature, your target can only go up as this feature goes up, or can only go down as this feature goes down, right? No wiggling effects like this, only this or this. Monotonic constraints, also easily included in this setup, and also a fun extra that you get out of there. And so XGBoost contains a whole bunch more of these interesting tidbits, such as being able to handle multi-output and multi-label settings, such as being able to use your GPU for training and make training extremely fast. I told you that XGBoost could be a bit slow, but actually that's already solved in version 2 of XGBoost recently. They have an implementation of random forests, even though they themselves use that. Normally you train gradient boosted decision trees, but okay. And because you can play with the loss function, they build in choices for loss functions that are worthwhile in different settings. For instance, if you know that you need to, that ranking is important, and you know that you are in a setting where we will only look at your top 10 predictions, and as many of those need to be positive as possible, then MSZ is not really a good metric to utilize, or binary cross-entropy, categorical cross-entropy is not a good metric to utilize, because that looks across the span of all the predictions. What do we care? We only care about the top 10 predictions. So then you can use other, more appropriate loss functions that learn to rank better, and just directly utilize them with XGBoost, right? So fantastic algorithm, fantastic technique. The other two are as well. Is it still worthwhile to utilize anything else? Well, yes, if you need high interpretability, a single decision tree can still be interesting. Logistic regression can still be interesting. If you would like to get like a view of, okay, what is the data itself capable of, then KNN is a good baseline as well. Random forests, because I like them, right? But that's more of a subjective reason, I guess. Other than that, naive Bayes, SVM, all these other kind of classifiers, mostly forgotten about. Not that important anymore. So learn these three, learn how to use these three, and you can tackle any tabular learning task. Even for something like forecasting and time series prediction, you're surprised the number of times that people just create lagged features, dump them into XGBoost, and that's your time series model. Forget about AutoArima and all that stuff, right? So it speaks to their versatility that they have become so commonplace and so popular and also work so well. Now, more from a theoretical point of view, back to our bias and variance discussion. Why do these things now work? So bagging, another nice thing is that bagging can be actually very easily done in parallel. If you have a random forest and you need to build 100 trees, each of these 100 trees can be built on a different machine. And at the end, you just send your trees to me and I combine them. So that's why for many distributed compute platforms like Spark, which we will see later, random forests are a very nice choice to implement, because this scales very well with the number of machines that you have. Right? If you have 100 computers, each of them can build one tree, and it will go 100 times faster as if you only have one computer. Right? With boosting, you can't, because that works iteratively. However, XGBoost and other techniques, they try to be clever, and they say, well, okay, but if you're building a single tree, both pathways of the tree can be built in parallel, right? Okay, yes, that's true. You can still speed it up through parallelism a bit, but it's not as extreme as what you would get with bagging. That's easily, embarrassingly easy to parallelize. Bagging guarantees a decrease in variance, right? So it guarantees a decrease in overfitting behavior, but it does not necessarily help you, and in most cases it won't, guarantee a decrease in bias. It will not make bias worse, but it will not necessarily help there, right? So this means that this is a nice technique to combine models that are located here, that have a high variance but a low bias, because then we can lower the variance. What are those models? Decision trees that we build all the way down. That's such a model. So it reduces the overfit of ensembles of complex models through the strength of diversity or randomness. Boosting, on the other hand, guarantees that it will decrease bias, but not necessarily variance. So this is nice to combine models that are located here. Simple models, like a decision tree with only 2 questions in it, right, or limited in depth. It will guarantee a drop in bias, but not a drop in variance. And in some cases, if you go too extreme, variance might even go up again. That's the little bit of the dangerous part of boosting. So bagging is a bit safer there. This reduces the error of ensembles of simple models through the strength of cooperation, the strength of predicting each other's mistakes. Well, it's not really each other because it's done sequentially, right? So it's not like a peer-to-peer kind of mistake network. It's more like every new party that I add to the group tries to fix the mistake of the group as a whole, right? It's not that you look at each other and you try to fix each other's mistake. Actually, it might be an interesting idea to... Okay, anyway. That means that with bagging, we go from here to the middle. We go from a model that's horribly overfitting on the train data. Let's say that these are my train data points. A decision tree that you build all the way is going to do this. Perfect predictions on the train data, but horribly overfitting. What happens now if I build 100 such decision trees, I average their predictions, but not all of them see the same training data, and some see points even twice? Well, the second decision tree might be something like this. The third tree might be something like this. Fifth tree. Sixth tree. Seventh tree. Eighth tree. Ninth tree. If I average these lines and I build more and more trees, the average is going to go towards, damn, no other color. Anyway, the average will be something like this. If I continue adding in overfitting models like this, once my average is stable, it's not going to move again, it's going to stay there. Right? It's not that this will become a flat line over time, it will become more and more the average line. Right? This is also why with bagging also 5 models is not enough. Right? But after 10, 20, 30, you get your average model that's not overfitting. If you add more trees, you're doing work for nothing, but it wouldn't harm you. With boosting, we say, okay, first model is an extremely dumb one. Probably even going to be, let's say, something like this. Second model, okay, what are the residuals? This. Second model You try to learn the residuals. And then by combining each of these models, what you get then is something that also starts to approach more and more a good model after a while. But then if you go further and further and you continue to try to learn on these small residuals that you now are getting, well, you will get closer and closer. And after a while, you are overfitting again and you're perfectly learning the training data, but are doing not so good anymore on unseen data. Right? You could plot this, you could say, well, let's also use a validation set like we did with a decision tree. And every iteration we will keep track of validation loss, and if it gets higher again, then we know that we need to stop boosting. Yeah, sure, that's something that you could do. So with boosting, you can overshoot the middle and end up in this regime again. Now, techniques like the ones just mentioned, XGBoost and so on, they do their utmost best to prevent this from happening, right? But it can happen. There is such a thing as overboosting. Just want to warn you a little bit about that. It's not like it's such a big deal if you use these modern approaches, but it can happen. With AdaBoost, you see it pretty clearly, actually. So there, if you continue to boost, orange is the validation accuracy in this case, right, not loss, but over time you see that the accuracy goes down again. It's an extreme case already, right, because here you need to build like 5,000 trees to kind of see this effect, but it is there. With bagging with a random forest, the validation accuracy basically stays flat, right? You need to pass this initial kind of zone because you don't have enough trees yet, but then once you have enough trees, this thing stays flat. So the effects are different. But it's pretty much a theoretical point. I mean, like I said, in practice, boosting is preferred. And the reason why boosting is preferred is that with bagging, remember, bagging reduces variance, but not bias. So you will get to a non-overfitting version of a model with the performance of that a fully built decision tree would give you, basically, but without the overfitting aspect. If you really care about accuracy, about performance more, then boosting typically will be able to give you a bit better of a model overall, with a danger of potential overfitting, but a little bit better performance measures. Not that the differences are extremely high, but they are there, right? So that's ensemble models, that's bagging and boosting, basically. The bread and butter of predictive techniques nowadays. Okay, then we are making great progress today. Probably not be able to see everything in here, but like the simple techniques we can at least do. So, we have just introduced both bagging and boosting, and I've told you in both cases it's a bit of a pity that you now get great performance, but at the cost of complexity and models that are not so easy to understand anymore. We would like to learn something as well from a random forest or XGBoost. Yes, you are making great predictions, but I also would like to know what you have now actually learned. What was important to you? Why do you predict yes here? Why do you predict no there? I would like to know that, right? It helps me to get trust in the model, and I also want to become a bit smarter as a stakeholder, as a human, as whatever, an expert, to kind of see what these models have picked up on in the data set. So some models are interpretable, and that's still like a good choice to reach interpretability is to use a white box model. So if you can get away with that, sure, utilize that. But many models are not. And typically you see that there is kind of a trade-off between model performance versus their degree of interpretability. With XGBoost already way out there in terms of not very interpretable, but a very good performance, and deep learning models even a bit worse. Arbitrary chart, I don't know why Random Forest gets a higher interpretability score than XGBoost does, because ultimately it's an ensemble of trees that it produces. But again, it's kind of to show the point. So what are techniques to still work with a very good performing model, like XGBoost or Random Forest, but get some insights out of it? Preferably, I would like techniques which are model agnostic, meaning techniques which I can apply on any sort of classifier, and not techniques that are closely linked to the working of the particular classifier that I've chosen, right? Like I could, for instance, in the case of XGBoost or Random Forest, what I could do is, if I want to kind of explain for a single instance which features are important ones, I know that I have my 100 trees. I could keep track of, in each of these trees, what are the features that they used in their splits whilst passing through this instance. And I could keep a count of each feature. How many times was this used by all of the trees? And then I could kind of tally that like this, right? I could even keep track of the splitting points. I could not only say age was used by 20 trees, but also which splitting point of age, 21 years, 22 years, 24 years, and so on. And then I could visualize something like this, and this would already give me some insight of, age seems to be an important feature. A lot of trees ended up using that for this instance. But the drawback is a little bit that, okay, this is, of course, you can only do this with ensembles of trees. If you have a deep learning model or something like that, or an SVM, there are no trees, you can't do this. So this is an example of a technique which is not model agnostic, right? Which is model dependent. Another easy way would be to say, what I could always do is I use my complicated model in production, but I will still build a relatively limited decision tree for explaining purposes. If I need to talk with my manager and they don't get how XGBoost works, or with the business people, I will show them the decision tree instead. That's called a global surrogate, which is okay, but of course it is only okay to the extent that that decision tree predictions are close enough to the predictions of that complicated model, right? If the simple model is too simple, it's even not worthwhile to use it as an explanatory model anymore, or to help to get an insight, right? So what are things you can do instead? Well, a typical question that you will get, there are different ones, but a typical question in this context will be, which features were now the most important one, according to your model? And again, you could use the trees to figure that out. With logistic regression, you can look at the coefficient values. But is there a general agnostic approach that we could take that works on anything, and it can give me an indication of which features are important? Okay, let's think about that. For tree-based ensembles, we could do that based on the mean decrease in impurity also, but again, that only works with GBM and Random Forest, so not really agnostic. Based on the position in the trees, same, we need trees. Well, there is a very easy way and a very precise way that we could come up with, and that's drop feature importance. That basically says, well, take your training set, for instance, or test set, whatever, and you know the AUC that you get of your model is 83%. And then take the same training data, but remove one of the features. Also in your test set, remove that feature, have the model predict for that test set without that feature in it, right? If you say, AUC has dropped, probably it dropped, right, to 78%. And then you know, well, this feature has an importance of like 5 points. And the more that it drops, the more important that feature is. But there is one thing you should do, of course, to make this work. To have a model predict on this data set without this feature in it, your model will say, oh, there's a feature missing, I can't predict, right? So you first need to retrain the model on the trained data without that feature. So you need to build and retrain the model multiple times, right? Drop a feature, retrain, drop a feature, retrain. This is a nice and precise approach and works on any sort of model, but requires a lot of retraining, which is why people don't like to do that. However, in some cases, like XGBoost, or if models are fast enough, you could actually try to set that up, right? And a package, for instance, that does so, low for importance, can do that for you. But it's still a bit rare to see exactly because it's a bit slow. Now, what's something else that we could do instead? We could say, maybe we don't need to drop the feature, but there is another way how we can take it out of the data set. And that's by the mechanism of permutation. And so permutation importance is an alternative where no retraining is required and is also still model agnostic. And the idea is very simple. Start again with your trained model, and you know the performance measure, AUC. And then, for each feature that you have, randomly permute the values of that feature. Right? Meaning, take the values and just shuffle them around. That's what this is doing. You could say, why don't we just impute it with the median instead? Right? And you also kind of take away the importance of that feature. Well, with permutation, there you at least retain a bit more the characteristics of the full distribution in that feature, right? Whilst still mixing it up completely. There is something to say to use the median instead. Maybe that would give you very similar results, right? With permutation-based feature importance, we shuffle. And we then ask the model, predict on this data set, please. Calculate AUC again. The AUC will be worse because one of the features got shuffled around, right? And the drop in performance, the drop in AUC, is then linked or is then an indication of the importance of that feature. And that's it, simple idea. This also takes, and this is another benefit of shuffling, if there would be an interaction effect going on, like there is the effect of R on its own, but let's say R is also in an interaction with another feature and also drives the predictive outcome. If I then shuffle R by itself, the drop that I will see in performance will be the result of taking out the predictive power of R on its own, as well as the predictive power that I got stemming from R and all the interactions with other features that it is involved in, obviously, right? So the importance score that you see is not just R on its own, but R and all the interactions that it was involved in, right? So this breaks interaction effects. This only gives you a ranking of importance, not how features drive the prediction or whatever, just a ranking of importance. Just an indication of if you would only use 3 features, what would they be? That's the sort of insights. If you don't like the fact that these interaction effects are included, you can also try to permute multiple features at once to zoom in on interaction effects. And then you have the option of keeping them together versus permuting them separately. For instance, here, I'm permuting R and F together, right? But not separately. 4 is 13, 2 is with 12, 11, 1 is with 10, 3 is with 12. Right? You have a question? It's likely going to do worse. I've never seen that case. If it does better, then for that feature, it would mean that it is actively harming the model. And that replacing the feature with a random bunch of numbers would lead to a better result. Then it would be an indication that the feature is harmful. But I've never seen that, right? But that's then what you would get from that. Theoretically, it could be possible, right? Nothing is kind of preventing the AUC to go up, but normally you wouldn't see that. Of course, models, if there is some stochasticity involved, your AUC might go from 91.56 to 91.57, right? But then it's more like a result of randomness rather than the feature really being harmful, right? But yeah, it can happen. So why permuting these guys together versus separately? If we would permute them separately, then you basically get the combined. So let's say the drop in AUC for permuting R and F separately then gives me an indication of the importance of R on its own plus the importance of F on its own plus the importance of the potential interaction between R and F plus the importance of R and any other feature plus the importance of F and any other feature. If I permute them together, right, instead of separately, then basically you get the importance of R on its own and the importance of F on its own. But now the drop does not include the importance of R and F in their interaction, because the pairs of values still show up correctly together. So if you calculate both and you want to extract out what is now the effect coming from the feature on its own versus the effect of the interaction between those two, you could then take the difference between both cases, right? This one minus the other one, and then this cancels out, right? And then you're left with this. You're also, and this also cancels out, right? Because you didn't permute over those guys as well. Very seldomly done. Mostly people will just permute a single feature. But theoretically, not a reason why you couldn't do it over multiple features, right? But very seldomly done. That's why also people sometimes think that you can't do it, but you can. Another thing that you need to be very careful of, and which is another reason why you might want to permute them separately, but to get more than one, is correlation. If you have two features like longitude and latitude here, for instance, I think I have a better, yeah, this is maybe better. Now, this I will come to later. If you have two features, longitude and latitude, and you permute them one by one, and you first permute latitude, it might be that your AUC does not drop a lot. And so your conclusion would be, latitude, your importance is very little. And then you permute longitude, and also the AUC does not drop a lot. And you would also say, longitude, you're also at the bottom of the list, right? Which would be the wrong conclusion, and the wrong conclusion comes from the fact that these two features are probably correlated. Depends a bit on the shape of the country and the data set, right? But let's say if you have a country such as Belgium, more to the south, more to the right, there is some correlation, let's say, between these two. Maybe not in every instance, but in this case, there are. Meaning that if I shuffle latitude around, it's not actually so harmful for the model, because the model is going to say, I still have longitude in that case that I can pick up on. So my predictions are not going to get that much worse. And if you take out longitude, not a big deal, I still have latitude that I can utilize, right? So in isolation, it seems that none of these two features are important. What would happen if I would permute both at the same time? Then suddenly I would see a huge drop in AUC, right? So be careful if you have correlated features, they might be hiding when you give them their importances at the bottom of the list. So how to prevent that? First do a correlation analysis, and for features that are heavily correlated, permute them together, right? Or take one of them out if you're training the model to begin with. The plot on the right-hand side, that's a random feature can get a high importance, right? Which is very strange. This can happen if you use an implementation of feature importances that does not use this permutation mechanism, but that uses decrease of impurity scores, right? And many old implementations utilize this version, but you should not utilize that. If you see that your importance is calculated based on Gini score or entropy score or mean squared error, mean decrease in impurity, don't use them, right? This is also the reason why people oftentimes thought, feature importances you can only get if you utilize a random forest or a gradient boosting model. No, you can do it for everything. Depends on if you use permutation-based feature importance or not. So these older techniques, they are biased. Permutation-based feature importance avoids this issue. And newer versions of scikit-learn, for instance, do implement permutation importance as well. But still, even for those, correlated features is something that you need to take care of. Right? That can still happen. That's still a danger of using them. The package that does this, I think, is the package mentioned. I think this is on the last slide. Yeah, or fpimp. Not the best name, right? But that package does this automatically. If you don't want to utilize that package, you just want to use scikit-learn, make a correlation plot. I think you can permute multiple features together in scikit-learn, if I'm not mistaken, but that's what you would then have to do, right? And so then you get like, latitude and longitude are actually together, and together they indeed do have the highest amount of importance that they get. Should you do this on the train set or on the test set? Well, both, right? It's interesting to do it on both because test set is in line with evaluation, like what's important when looking at unseen instances. Train set is more in line with what has the model learned, what does the model believe. Generally, you expect them to be similar. If they are different, that's also an interesting insight. Weird, for unseen cases, other features are important than the ones that I saw in my train data. It's already kind of a warning that you get there, right? So do it on both your train and your test set if you can. Another mechanism then, let's say we know that age is an important feature, but we are wondering, okay, but how? Is it if age goes up, you're more likely to be a fraudster, or if age goes down, or maybe the pattern is more complicated? In other words, I want to see a plot like this. Depending on the value of age, what's the probability that my model predicts? Here it's rescaled between minus 0.5 and 0.5 or something, but that's basically what the y-axis shows. What's the probability that people in this age group get? Ceteris paribus, kind of meaning, okay, the other features should not matter, right? Only looking at age on its own, how does this drive the prediction of this model? So how do we ask the model this? Well, again, pretty simple. We need to give it all the features. Again, we could retrain the model using age only, but that leads to a new model. It also does not include interaction effects in there, so it probably will be a different model and so on. Might be overfitting because I only gave it one feature. So I would like to prevent having to train new models. I would like to do it with the model that I have. So what I do instead is I have age, or I keep age as is. I don't touch age. I could also say, okay, let age vary between the minimum and the maximum, right? But then again, there might be age brackets that do not appear in your training data, and if you would just then define a range from min to max in age, you will also include those gaps that you didn't observe in training whilst doing this. So typically we say just keep age as is. But then for the other features, we are going to replace their values now, and now we do follow this idea that I said just previously. Use the median for the continuous features, and use the mode, the most occurring value, for the categorical features. Again, this is not without danger. This is not perfect. Do you really prevent here from extrapolating in your training data? Not fully. It's not because you take the median of a continuous feature that that median also showed up in your train data, right? Might be that you have numbers over there, but not in the middle. So it is a bit with danger, right? It's also not a guarantee that these combination of values occurred together. So we are taking a little bit of risk, but that's the way how we do it. That's the way how we basically say, okay, what would my model say if I try to create what you could call like an average instance, like the average Joe case, except for age? That's the one that we will vary. And then what does my model think about that? So I ask my model to make predictions, and those are then exactly the predictions that you plot on a plot like this. Now you can also use the permutation approach here instead, right? That's option 2. And here we say, well, for each distinct value of h, right? So 28 is one value. Take all the instances in your data set and ask the model what the prediction would be for those instances if they all would have that value for h, right? Then you're not trying to create an average Joe except for h. You're trying to say, well, what if we take everybody and we make everybody 28 years old? And then we make you 21 years old. And then we make you 42 years old. And I ask the model, predict on all of them now. Predict on all of them, predict on all of them. So now, for each value of h, you get multiple synthetic instances that you create. How to combine this into a single value? Well, average the predictions, basically. Or you could even draw little box plots now, right? Now, with your plot for value 28 of h, you could basically say, well, this is the range of the predictions of the model that come out. And you could draw curves like that. This is a bit more of a robust approach, less commonly implemented. Again, is there something preventing you from doing this with more than one feature at once? No, right? And then you can make plots such as on the right-hand side. You get like a contour plot of predictions of your model over these two features that you have. When is that interesting? Well, to spot interaction effects, right? Again, it might be that these two features on the left-hand side, well, this one does have a strong impact, right? The prediction changes a lot. But this one is kind of relatively flat, not such a high kind of change depending on the age of the house. But then if you take both of them together, well, actually then you see that the age of the house does have a very large impact, but it's dependent on the average occupation, right? If AV-occup is low, then the age of the house matters a lot. If AV-occup is 4, then basically the age makes almost no difference, right? So by, again, making plots out of more than one feature, you can look at the interaction effects more closely, more deeper. This also means that if you see a flat line, like here, that absence of evidence does not mean evidence of absence. It might happen that you have a feature that gets a high importance score coming from permutation importance, but when you make a partial dependence plot, it shows up as a flat line. Why is that? It's an important feature, but it doesn't change the prediction. Well, then that is strong evidence that that feature is probably involved in an interaction effect with another feature, right? You could also say, well, why do I make partial dependence plots? Why don't I just look at the train data directly, make bins for age, and then look at the percentage of cases that are positives in each bin? You would get the same kind of plot, right? Well, again, it's interesting to look at both, because you might see from your data that there is indeed a drop in sales for customers in a certain bin, between 30 and 40 years old, let's say, and in your partial dependence plot, it's a flat line. That shows you that age alone is not a sufficient explanation, right? And that there are other things that play a role as well, that age is in an interaction with other things. Maybe we simply offer less products to that age group, right? Then it's not the age that drives the sales, it's our offering that drives the sale. So again, it's interesting to look at the data directly, but it's also interesting to look at what is my model telling me, right? And that's why we also make partial dependence plots. There we have some ideas of even doing it with more than 2 features, but you get plots that are kind of difficult to interpret, so that's not oftentimes done. Okay, the next type of interpretability technique are ICE plots, which is a kind of a variation of partial dependence plots. So what we did before is we had a look at these partial dependence plots, and we saw how they were made. We basically create or we keep age, or we had 2 options. We either keep our feature as is, under observation as is, and we impute the median and the mode for the other features, or we generate synthetic instances, one with age 28 and one with age 29 and so on, and we keep everything as is for the other features. But in any case, we could then make a curve like this one to kind of get the effect of a certain feature or a combination of features on top of or related to the prediction that our model makes. We also saw that it can happen that you see a flat line in a partial dependence plot, so that it seems that no matter what age is, for instance, that it has no effect, even although your feature importance ranking shows that it's an important feature. And then we already saw, okay, be a little bit careful with this. This is probably then the result of the fact, or a result of the fact, that age is in an interaction with something else, that age alone is not a sufficient explanation. Right? It's rarely that you would see like a complete flat line, but be aware that a partial dependence plot only shows you a ceteris paribus effect over that one feature, does not include potential interactions that that feature has with other features. If you would like to see that a little bit better, then the individual conditional expectation plot, or the ICE plot, works a bit, or is a little bit of an improvement. And the way how we set that up, it's actually quite similar to what we were doing for a partial dependence plot option 2. Again, let's say that I want to inspect age. What I do is, again, I generate synthetic instances. And I will say, okay, what are the different ages that I saw? I saw 21, 28, 32, 42, and so on. So, okay, let's now assume that all of the instances that I have in this data set, that they have an age of 21. And then again, let's assume that they all have an age of 28. And 32, and so on. So you depivot that, and you basically generate a data set like this, just as what we did for the partial dependence plot. Except with the partial dependence plot, we then said, well, let our model predict now for all of these lines, and then we're going to average based on the distinct values for age. So take the predictions for all of the instances where the age is 21, average them together, and that then became 1 point here for age 21 in our partial dependence plot. But what I says, or what an individual conditional expectation plot says, is, well, we don't actually have to throw away all of these different instances that we have created here. Why not simply show them separately instead, right? Because here now, for one instance that you had in your original, you have a variation where you make them 21 years old, 28 years old, 32 years old, and so on. And you have that for all of your instances. So why not show your different instances as different lines, where you vary across age or where you vary across the feature of interest? So we can let our model predict just like before, but now we show just all the instances separately as different lines. And you might say, well, that looks a little bit like a mess, which is true. So 2 additional steps can be done as well. First of all is, let's center them so that they all start here from 0, and the rest of the movements are relative to that first point. You could also center at the end, it doesn't really matter, but typically you do it, you make the first point the center point. And then you can also make the average line, which is then comparable to what you would have gotten with a partial dependence plot a couple of slides back. What benefit does this now have, in the sense that this now shows you kind of all of these different black lines here as well? Well, you can better spot the presence of interaction effects in this case, right? Again, it might be that this yellow line is relatively flat, but that all the movements of the instances separately of the individual conditional expectations, that they show you a variety of behavior. If they're all flat as well, then you kind of know, okay, this feature has no impact, has no effect. You also wouldn't expect it to be a pretty important one in your feature importance ranking. But here, for instance, you do see, let's say that the x-axis is age here. You do see indeed the general trend is like this, so the probability doesn't move, goes a little bit down, but then at 50 years old, there is an increase for a bit. So people between 50 and 52 years old, there the probability jumps up, and then it stays there for the older people as well. But it does not have the same impact depending on what your other features then are. It does not have the exact same impact depending on the other things that this value of age co-occurs with, right? For some instances, we do see that already in the beginning, they jump up heavily. For some instances, we see that this drop here is way larger than what the average effect is. So probably there is still an interaction going on apart from age alone that kind of drives whether an instance falls more in kind of this lower behavior or falls more into this higher behavior, right? Then figuring out what that other feature might be, there are strategies for that as well. What you could do is you could then go over each possible pairs and make a plot such as this one, and then until you see the interaction from showing up, right? Like we did here as well. So this is also a pretty common technique to get like insights in terms of how does a prediction behave across values of a feature under study. Then there is LIME. LIME stands for local interpretable model agnostic explanations. And what this basically does, it used to be pretty popular for a while. It's still relatively popular, but maybe a little bit less so than a couple of years ago, and I will tell you why in a second. But the idea is pretty neat. It basically says, well, we will build a local surrogate model, and we already saw a global surrogate model that was, well, you have a complicated model, it's hard to explain, so in order to explain it, I will build a simpler version of the model. I will build a decision tree instead of a random forest, because a decision tree I can kind of explain. I will lose some predictive power, but at least that will be easier to explain. LIME does the same thing, so it also builds a simpler model, but it keeps that model very locally around a particular instance. It doesn't try to build such a simpler model for the whole data set. It only tries to do so around an instance of study. So here you start from the question of a user saying, well, this instance, it gets a very high score according to your model, or it's kind of on the edge, it's like 50-50. Can you explain what would have to be different about this instance to make it flip from a no prediction to a yes prediction? Or to make it flip from a cat prediction to a dog prediction? Or to make it even become a stronger yes prediction? Right? So you're looking for that kind of explanations. And you're looking for them by changing features. Like, what would I have to change in the features of this instance so that I would get your desired outcome? Of course, you know that you will always be able to find multiple such explanations. By playing around with the features of an instance, of course, you can get your model to say different things, right? Of course, what you're looking for is the explanation that is the, you could say, the most regularized one, meaning the one that makes the least amount of changes. Least amount of changes, maybe you only want to touch a minimum amount of features, right? And maybe for each feature that you touch, you only want to move them slightly, or as slightly as possible, right? So you're kind of looking for an L1, L2 sort of behavior there. So that's what LIME does. How does it do so? Well, let's say that this is our data set, easy to see, two-dimensional, right? But it's to show off how it works. And we have built a pretty complicated model, let's say a random forest, with a decision boundary that we can draw here because we're working in 2 dimensions, but normally we wouldn't be aware of, right? In higher dimensional space, drawing that decision boundary, well, you could do that, but you will not be able to look at that. And we say, well, we have a certain instance here, let's say this dot, and it's like a prediction, it gets like 78%, whatever, and we want to know, okay, why? What would have to be different here about this instance for my model's prediction to flip from yes to no, from yellow to purple here? And of course, because you know the toy example, what you see here, I can only play with either x1 or x2, and you can already kind of guess that probably x1 will be the best one because I only need to increase that a little bit and you go across the decision boundary. Right? But normally we don't know that. So how can we know that? First, we take our instance that's at our center of attention here, and we generate synthetic instances around it. Why? Just by, or how? Just by uniformly sampling min-max in the feature space. So just generate 1,000 instances. I'm only interested in those synthetic instances that are pretty close to my instance of observation. Right? So I'm going to give all my synthetic instances a weight. The closer that they are to my original instance, the higher of a weight that they get. Right? You can put like a Gaussian kernel on top of that to do that. But basically, once you're too far away from the instance of observation, you don't matter anymore. Right? I could even delete that synthetic instance because its weight is so tiny. But you get instances like these. I then ask my model, it says here you can then sample again from that. Either you do the sampling afterwards or you do the sampling first, whatever. You end up with a bunch of instances around my observation that interests me, and each of them have a weight based on closeness to that instance. And I then ask my model, well, predict, please. For all of these guys, what do you think? So my prediction is going to be, in this case, I'm doing binary classification. My predictions are going to be scores between 0 and 1. So that's what the color here represents now. That's that score that my model has given all of these synthetic instances. So okay, now I have a bunch of synthetic instances, each with their score. What do I do next? Well, the next step is, now I'm going to use this as a training set on its own to train a model locally. Locally, why? Because it's only looking at instances that are nearby my instance of observation, right? Which model will we pick? Well, it needs to be a simple one. We also know that we want to make the least amount of changes. We also know that this is going to be a regression model because the output is now the probabilities coming from my black box model, right? It's not zeros and ones, it's scores between 0 and 1. So probably lasso regression is not a bad choice. Then I can really regularize heavily and make sure that it only touches or uses the least amount of features possible. And I basically ask it, well, predict me the probability that my more complicated model gave me, but you only need to do it for these instances that I sampled around the instance of observation, right? Are the weights still used here? No, right? The weights are only used kind of in this step to do the sampling. Basically what this means is that you want to give a higher likelihood that you include instances closer to the instance of observation, right? So you use the weights to sample there. And then you get a decision boundary that looks, well, in this case, it looks like complete vertical stripes. Why? Because we're doing a lasso regression, and it has basically said, well, the best thing for me to do is just use feature x1. x2 I don't even need to use, right? It doesn't give me any additional loss improvement, so just use x1. The middle of the decision boundary, the 0.5, is over here, and then you can go left or right. And then from this lasso model, we basically extract our explanation from, because then we can ask this lasso model, okay, currently my red instance here gets a score of, I don't know how much it was, 0.45 for instance. How could I make it larger than 0.5? Well, if you add a tiny bit to x1, then it moves to the right, and then my prediction would flip, and that's your explanation. And then you can kind of agree with that explanation and go, oh yeah, now I see, yeah, that makes sense. Or you can disagree, of course, but at least you have an explanation. So this decision boundary of this explanatory local model approximates the decision boundary of the black box model around the instance under study. That's the idea of Lime. The nice thing that they did is that they also had solutions for non-tabular data as well. And again, how would that work? Well, what's the key step here is we need to come up with a way to generate synthetic instances. And we need to come up with a way to generate them that we can generate these synthetic instances close to the original instance, around the original instance. So with tabular data, we can do that by first generating uniformly and then just sampling using this weight. But how do you do that if you have an image, for instance? Or how do you do that if you have text? Well, for an image, Lime suggests, but you could actually come up with your own ideas as well, right? But the recommendation that they then gave is, well, what you can do is first apply k-means on your image to kind of identify super pixels, groups of pixels, right? And then to generate synthetic images, if this is your original image, every synthetic image is going to take out, gray out one of these clusters that we found, one of these blobs of pixels that we found. It's going to mask them, basically, right? And then those are the synthetic instances of that I generate. How does that work with a lasso model, right? So in this case, I'm not going to be able to draw this doggy as beautiful as that one, so I will draw like a house with a sun and a tree. And so your k-means identifies, okay, all of here, those are all yellow pixels, and then these are all kind of green pixels and brown ones, and this is a red house, and this is a roof, and then maybe you have like other clusters going on like this. And then from there, I generate synthetic images where I say, well, you're exactly the same, except one cluster is kind of grayed out, right, and replaced with the average pixel value instead. And maybe every synthetic instance does not need to gray out only one cluster, but maybe some of them gray out multiple ones, right? Maybe here, both this part is grayed out, And this part over here is grayed out and the rest is the same. Then I ask my model to predict again. What do you think? Do you still think that there is, or one of your top predictions on this image was, I believe this is an image of a house, of a tree, sun, and then some other things. And I want to verify, you think this is a house with a high probability? Strange, right? I don't believe you, or you need to give me an explanation for that. So then I generate my synthetic instances and I ask my model to predict how much do you think that this is a house, right? So here probably it won't have dropped a lot, right? It will still be high because it still sees a house. For the images where I blanked out the house, it's going to say, well, house, not anymore, right? I don't see that anymore. Then you ask a lasso model, predict me this probability of my black box model again. But what will my features be now? Well, my features, x1, x2, x3, these all correspond to, did you blob out this cluster, yes or no? So you have as many features as you have clusters that you identified. And you can put a 1 if you blob it out, and a 0 if you left it intact. Right? And then from there, Lasso is going to build, and it's going to say, well, I can't use you heavily regularize. And it's going to say, well, the only feature that matters is x3. Well, this feature x3, well, it's the one that corresponds with this group of pixels. And yes, indeed, if we blob that out, if we mask that away, that's indeed where the house is. So I agree with the explanation, and I can indeed verify that my model is looking at the correct things, right? And that's exactly what you then see here. This is a model that says I see an electric guitar, I see an acoustic guitar, I see a Labrador. Okay, why do you see a Labrador? Well, if you hide away these parts, right, and the image actually shows the opposite to us, right? But for the model, what we actually do is we hide away the head and this thing on the bottom, and then it doesn't see a Labrador anymore. But then to show us the explanation, we can of course show it in this way, and we only show the parts that were important to the model. Right? And then you can go, oh yeah, indeed, makes sense. My model is looking at the correct things. Similar for text, but there you play with synonyms, or you remove words from a document and things like that to generate synthetic instances. And then same thing, a feature describes whether you remove the word yes or no. Why is this difficult to use? Well, a neighborhood around your instances, especially with tabular data, the question is a little bit, how large should you go in terms of including these synthetic instances, right? Very close only, but then you're looking very locally, right? And your explanation is going to suffer a bit from that. But if you increase kind of the range in which you look or in which you generate your synthetic instances, then probably you also feel that your local approximation of the decision boundary, you're going wider, maybe that will be more difficult. So you need to strike a good balance in terms of how close you stick to that synthetic instance. Yeah, the choice of Lasso is a bit arbitrary. You could put, or you could utilize another model as well, ElasticNet, where you put in both L1 and L2. How much you regularize that model will of course kind of drive Lime towards giving you smaller, easier explanations, but maybe not perfect ones, versus explanations that are a bit larger, but more representative of what the underlying model is actually doing. So the fact that it comes with a bit of these tuning things, and the fact that you can kind of get different explanations, how you set up your Lasso regularization and so on, is the reason why it's a little bit less commonly utilized nowadays, because it requires some fine-tuning, it requires some careful usage. But the idea itself is pretty clever. Then, the most popular one, in terms of explanatory technique, still very widely used, especially on tabular data, this is the default one, is Shapley values. And it's named after the, after Lloyd Shapley, who came up with this idea of Shapley values, won the Nobel Prize for that. Was not concerned about machine learning at all. Didn't know about that. He was concerned about game theory. And more specifically, he was looking for a way that, let's say you have players and they play in a cooperative game, so they play together, right? They all work together in a team to get a certain outcome. How can you assign in a fair way, mathematically mainly, a fair payout to each of the players in that team? to each of the players that cooperated. So let's say that we will play a game, right? And it's not a competition, so here we're more looking at the contribution of players to a team, in one team, right? So maybe this is like a scavenge hunt. The world has collapsed, and I send out 5 of you, and you come back with things that you've collected, and I'm kind of wondering, okay, how should the loot be distributed across the 5 of you, right? How can I assign who did what? So I have 5 players, and I want to know the marginal contribution of each player to the team. Now, what I could do, and this is why this becomes a little bit more of a hypothetical, well, you could set this up in real life, right? I could say, well, let me send to know how good each of you is. Let me send out 1 of you by yourself. So a team with only 1 player, player A. And you come back and you get a score. You obtain a value, right? And the value that you obtained is 6, right? And this value function is the characteristic function, it's the score function. But if I send A out by themselves, they come back with 6 points. Okay, then I add player B to the team. So I have A and B, I send out that team again together, and they come back with 10. And then I say to player B, well, player A alone had 6. Now that I've added you, you come back with 10, so you have a marginal contribution of 4. And then I add player C, and I send them out again, and they come back with 12, and I tell C, you have a marginal contribution of 2, right? It's almost like a Mr. Beast video. What would player C say in this case? If you would do that, they would say, well, that's unfair, because you only added me after already having added A and B. You never give me a chance to go out by myself. Maybe I would already have brought 10 by myself, because what you don't know is you send out the 3 of us, but now A and B, they weren't doing anything. I was doing everything, right? So, okay, you say fair, that's a good point. So to really know the marginal contribution of a player, I should kind of go over all possible orderings that I can add C in this team, right? So indeed, if I added C before B, right, maybe I could already have, or instead of adding them as the second player instead of B, I also get 10. So now then C has a marginal contribution of 4 and B of 2. So basically what I need to do is I need to go over all possible formations of a team, right, and average their marginal contribution. So I need to go over all possible ways where I can make a team that includes player C, minus the teams or the combinations that do not include player C. Now, luckily, what does not matter is the order in which I added the players before C. That doesn't matter, right? Whether I did A, B first, or B, A, at the end, I get a team with both B, A, and C. So it's the fact that it's B and A that are in there together with C that's important, not the order in which I did my previous steps. So I can skip that, I don't need to go through that. And what also doesn't matter, but that's the same thing, like for the team that did not include C, well, yeah, same thing, right? A, B, B, A, that's kind of the same. That should give me the same result. Okay, so then I could set that up, and then you get this formula, which looks a bit scary, and it is a bit scary, right? So the marginal contribution, the Shapley value, as it's then called, right, for player J in a team, is the sum of all the possible permutations, or the sum of all the subsets here that you can make from the other players, but not J, right? So in my case, I had 5 players, all the possible subsets are A on its own, B on its own, D on its own, E on its own, and so on. And then A and B together, and then A and D, but not C, A and E, and so on. But I have already done A and B, so B, A is not a separate thing, right? Because I just set it the order, doesn't matter. And then I say, well, I have 2 versions, basically. Take the value that this subset gives you with your player C included, minus the team without that player C included. Right? And the difference is then the marginal contribution for player xj, and you go over all such possible combinations, but we want to take the average, so this is where the bit of the hocus pocus comes from. This is basically the normalization that we need to do. We need to normalize based on all the total numbers of possible teams that we have. These are all the permutations of players in the team, times all the permutations of residual players. And then you get a value or a score for our player. Okay, what is this in machine learning? Well, in machine learning, when we make predictions, we could also say that the features and their values are playing a game. In other words, the prediction result of my model is now the score, the probability that you got, or the continuous prediction that you got. That's the score, right? And my players are the features with their values for a specific instance, right? Every instance that is being predicted on is one little game that is being played. So it's not one game for the whole data set, it's for each instance separately, right? And so there I could also ask, well, the value, right, for a certain feature is then the same thing. Can I ask my model to make predictions on all the combinations where I include this feature, minus all the combinations where I do not include that feature? And then the difference of that is again, or the average difference of that, is then again a value that I can assign to that feature. Here, well, the idea is that we do minus the average prediction. It's also a small kind of difference. Because here, of course, if you think about the prediction game being played, right, everything always starts at the intercept. Everything always starts with the average value, right? Because then you basically are not including any features at all. If you just have an intercept model, you don't have any players, that's actually your baseline score, right? That's your 0 in our case, right? And it's how you deviate from that intercept prediction, that's here where the features come in, right? They arrange the deviation from that intercept value. One problem is that typically we have a lot of features, and so this thing explodes. Every time you see like these exclamation marks, that's not gonna work. And another problem is, well, in this case, what we would actually have to set up, right, is we have to ask our model, well, what's your predictions if we include these features, but not these other features? And again, we saw last time that a model always needs to get all of the features, right? If we would want to do this, we would basically have to train separate versions of the model each time, right? If we only want to use features A and B, well, then we need a model that's been trained only on features A and B. So again, that's work that we do not want to do. And again, you could then say, well, use the average or the median value for that feature, but it's not super stable. We had kind of the same issue with permutation feature importance as well. So here, we're going to set up a very similar trick as the trick that we utilized to calculate permutation-based feature importance. We're also going to create permutations in a way. We're also going to create synthetic instances. So what we do here, well, this is the formula. We're going to sample m rounds. So we're just going to do a Monte Carlo sampling. And what we will do is we will take the difference of what does our model say, for instance, xm plus j, minus what does it say for minus j. And j is a chosen feature that we are interested in, and x is a specific instance that we're interested in. So how do we create this plus j and this minus j version? That's the thing that we need to figure out. So let's say that I have an instance x. So this one is fixed with recency, frequency, monetary, debt, age, and income features. The feature that I'm currently trying to calculate the Shapley value for is f. So I'm currently looking at this instance and this feature with its value, right? So you can do it for the others as well, but I'm looking at x and f. And the idea is that we, every round that we do this sample, that we pick another instance from our data set at random. That's this z, a randomly chosen other instance. And the two variants that we create, right, the plus j version, for f, there we're always going to keep the value that my instance originally had, 2. And for the minus j version, I'm going to replace f with kind of the feature from a randomly chosen other instance. Like, it's like, what if I use your real value, and what if I just use a random value picked from my data instead? Right, so that's what I do for f. What do I do for the other features? Well, there I randomly select a subset of them. right? So my other features are R, M, debt, age, and income. And I maybe select R and debt randomly from them. Those are the two that I pick out. So for these two, for R and debt, I use the values of X, 5 and 100, for both of these variations. And for the other features, right, so M, H, income, there I use the values of Z instead. So for M, 500, for H, 36, for income, 3,000. And so that's how you create like these two half sites, these two half instances, right, where they kind of, we randomize, but they meet in this value or in this difference of F, that we always keep the same, right? And the idea is not that we set this up one time, but that we do so thousands of rounds, right? And then it can be proven that the average that we get after M rounds, whoops, come on, yes, approximates the true Shapley value. So if you do this enough, right, then you get the true Shapley value. Shapley value of what? Well, you get the Shapley value for that feature, but also specifically that instance, right? So it's not that you get one value of importance for each feature here. No, you get how important was that feature when we predicted for this instance. So what I can, or what I do see from this, at the end for one instance, I will have values, and that's what these bars here represent, for all of the features and their values for that instance. And then basically the interpretation is, well, your base probability, your average probability that this model gives you is 0.1, right? And so what was the impact of these features to go to the final prediction of 0.4? Well, BMI had a slight increasing impact, increased the probability. So did BP equals blood pressure equals 180, also had a slight positive impact. Age also had a huge positive impact, the fact that you're 65 years old, right? But the fact that you're female had a downwards impact. But altogether, we went from 0.1 to 0.4 through these features and their values. Does that mean that age equals 65 always has an impact of plus 0.4? No, for this instance it had, right? So it's the contribution of the features with their values for the prediction of a specific instance. Here you can see something similar, right? Same thing, but plotted in a little bit of a different way. This is for a regression problem instead, right? And I can see that by looking at the model output, which is now not something between 0 and 1, but it's 24.41. And again, I start here with my base value, the average prediction of 22.34. What was the impact of all the features? Well, here they're plotted kind of centered around this model output, but it's the same interpretation. You have features that moved you to the left. Now, those are these features, but their impact was not so high, or their contribution was not so high. But these two features had a high positive effect, right? So ultimately, you ended up a little bit higher than the average value. So this gives a deep explanation and interpretation for especially tabular models. If you then want to summarize this, we actually can in a simple way. What we can do, and this is the typical plot that you then always see, is, okay, for every instance and for every feature, right, I have the Shapley value for that feature on predicting that instance. So for every feature, for every instance, I can put one dot on here. Every dot here is one instance, right? It's the same instances for each feature, so you have the same number of dots across all of the rows here. The position on the x-axis here is that Shapley value, negative, downwards impact, or positive, upwards impact. On here, probably on a binary classification model, I guess, because the Shapley values are between 0.3 and minus 0.1. The color that I give these dots. That's related to the value that this feature had in that instance. Right? So here I can kind of then start to see, okay, hormonal contraceptives. When this feature is red, so it has a high value, then in general I see that it goes to the left here, so the impact on the prediction was negative. So the more hormonal contraceptives that you take, the less likely you are to get, what would this be, some type of cancer maybe, something like that, right? Age, it's a bit of a mix, right? But generally speaking, we do see that as age increases, that the impact gets higher as well. We can then sort these features based on, well, let's take the averages or the sum, because anyway we have the same amount of dots for every feature anyway. So let us take the sum of the absolute Shapley value for each of these dots and put the one with the highest sum on top and put the one with the lowest sum on the bottom. And then this is exactly the same as a feature importance ranking. The most important one is at the top, the least important one is at the bottom. And that's how you read this. It becomes even more fun if you then start playing around with multiple features and you plot them kind of in this way. Like, okay, let me then take these hormonal contraceptives, and is it a different one, or no, it's indeed this one? Oh no, it's the top one, it's the most important feature. Hormonal contraceptives years, probably the number of years that you took hormonal contraceptives. One lady in here for 30 years, okay, fine. For each of my observations, on the y-axis, I use the Shapley value, right? So I use the position that I had here, but now I put it on the y-axis and I put the actual feature value on the x-axis. Well, now you get something which is very close to a nice plot or a partial dependence plot. This shows you the behavior of the model over this range of years, right? And then you can say, well, maybe it's in an interaction with something, right? So let me bring a second feature just as we did before for a partial dependence plots. Let me take in the fact that you had an STD, yes or no. Green is yes, blue is no. Indeed, for the blues and the greens, there is a slightly different effect going on here. So because we now have a importance value, not just per feature, but per feature per instance, we have very nice ways to combine all of this and to show all of this. So no wonder that this has become the most popular interpretative technique in industry and also in research in a lot of cases, especially for tabular data, very easy to execute. With other types of data like graphs, maybe a bit harder to do, but for tabular data, this is pretty easy. It doesn't mean though that if you ask someone, it's always a good exam question, it's easy to get like a general idea of how do you build this, but the details are important. The fact that the Shapley value is this thing in the x-axis, that the feature value is the color, the fact that the scales are the same, red is always the highest red and blue is always the highest blue in each of these rows, probably means that the scaling here is done per feature rather than globally, right? Or the normalization or the min-max ranges. But that's basically what's going on here. So conclusion. Conclusion is, interpretation is important, obviously. If you want to read more about this, a fantastic free book that contains the interpretability techniques that we have seen, but also many more, is this one. It's completely free. It's very well written by Christoph Molnar. One of the best books on interpretation that you can find, bar none. So check that out. I also listed a couple of other links and packages that you can check out that implement the techniques that we have discussed. Most important one is the one that implements Shapley values, which is SHAP, right? And that's also where these typical plots come from, right? They come with this from this package. And they have some other plots, like a standard feature importance plot and so on, that you can then extract. Obviously, we've seen how to do that. But this is a very popular package. They have specific implementations depending on the model that you're using. There are optimizations that you can do if you know that you will work with a tree-based ensemble, or you know you will work with a particular type of a neural network. Then you can get these Shapley values in a quicker way than you would have to do by going back to this Monte Carlo permutation stuff. So they have optimized versions of that as well. That sometimes leads people to believe that Shapley values are model-specific, but it's actually model agnostic, as we have just seen. Any model that can give you outputs, you can use Shapley values with, right? So it's not specific to a particular type of model. Another interesting idea, as kind of a closing thought, is we have seen that if you think back of how random forest worked, or how a gradient boosted model worked, at the end we said, well, in both cases you kind of just get a bunch of trees. That's your final model. And we let each of them predict, and we average their prediction, and then we try to utilize an interpretability technique to kind of figure out which feature is important and so on. But is there really no way? I told you you can print out 100 decision trees in a big book, but no one is going to understand that. But of course, the question that you could also ask is it actually so difficult to, instead of trying to print out 100 decision trees, couldn't you just merge them back into a single huge decision tree again? Right? And again, this took a while for people to actually figure out, spectacularly long actually, but indeed you can do exactly that, right? So if you look about, if you have 3 decision trees and their decision boundaries look like this, of course you can overlay their decision boundaries, their decision boxes, or cubes or hypercubes on top of each other, and then you basically get a situation like this, where each of these rectangles that you see here is a leaf node in a merged tree, right? So you can easily, by overlapping the leaf nodes of the separate decision trees, you can easily merge and construct a global decision tree again. You could then even go a step further. You might say, well, it's going to be a very deep decision tree because you have a lot of leaf nodes in that thing. True. But again, you could maybe apply a form of pruning, where you say, well, if I look here in my feature space and I look at 2 decision boxes that come from the way how I created this overlap here, and if the decision boxes touch with one another, right? So they share a dimension, and the values that this is a regression model, so the values that I would get in both these leaf nodes, they're not far away from each other, then maybe I can just merge these 2 boxes together anyway, and I can reduce the number of leaf nodes that I will get in my merged decision tree. And maybe its performance will still be relatively in the same ballpark as what I got with the ensemble model anyways. And indeed, turns out that that's what happens, and that's what you can do, right? You can perfectly well create a single decision tree out of a bunch of decision trees by following this approach. This was implemented at a time by a company called Wagtail Labs, but they went defunct, sadly, pretty rapidly. I still think you can find the source code floating out there, but a fun weekend project is to try to implement this yourself, obviously. Yeah, just goes to show that sometimes clever techniques can also show up in terms of how we interpret these things or how we play with these things. But anyway, that's it for interpretability for now.